Good afternoon, everyone. We're so excited to be here, and on behalf of our team at Clemson University, we'd like to show you our approach to supplying clean energy to the solar plentiful New Mexico State University campus. So I'd like to highlight our team approach. Next slide, please. I want to take this moment to highlight all the multidisciplinary team members that we've had that made this possible. And I want to introduce myself. My name is Pamela Lowell, and I'm joined here by Matthew Allison, Benjamin Hennigan, and Daniel Carrillo. Next slide. So our approach to the competition, when we started this competition, we knew we'd have to prioritize a strong sense of personal work ethic, an equal contribution from all of our different sectors. But that being said, we also had to rely on each other to work collaboratively, and we held group meetings to bring all of our solutions together. Next slide. When it came to our system design, the foundation was getting great data and accurately modeling it. So we used the National Renewable Energy Laboratory's extensive hourly installation database, and we used that to build an idea about the type of production that we could see at NMSU. We used satellite imaging and Aurora software to size all 10 campus rooftops and the additional solar farm. And then we worked to find the most accurate utility power rates for both on and off peak hours, so we could prove that our solution would be the best move for NMSU, both environmentally and financially. And then we determined that our high efficiency rooftop system would overall be rated at 4 megawatts, while the solar farm system will be rated at 8.2 megawatts, leading to a total of a 12.2 megawatt system. And the rooftop and farm would meet daytime and nighttime demands with storage capabilities of 12 and 35 megawatt hours respectively. Next slide, please. When all was said and done, we expect that our efficient and longevity-oriented approach will allow the network to operate for 20 years, and then the components will have to start being replaced. Next slide. And now we're gonna get more into the technical side of things. Next slide. So our design approach is something that we've dubbed the 60-40 approach. So that means that our daytime load is only met by 40% of the DC rooftop production, and the remaining 60% is then sent to the battery. So if there's any deficit in those during those solar hours, the deficit can then be met by the farm system and the farm battery. Any daytime surplus after charging the battery can then be sold back, and the only real deficits are going to occur after the farm battery has been discharged. So this allows us to pretty conveniently only need to purchase from the utility at night, and at night is the absolute lowest buying rates that are available for NMSU. So that's going to be a huge plus for us overall. Next slide. So to make our plan happen, our design uses high efficiency solar panels with a 22.7% efficiency and a 370 watt peak power rating. And we think this is appropriate to meet the large demand and to be mounted on the rooftops. So using these modules and the NREL hourly ambient temperatures and insolation values for the most recent year that we have available, we were able to develop a derating factor and analyze the efficiency and the resulting production during all different types of weather conditions that have happened during the year 2018. Next slide, please. So here's where I'd like to show how we utilize the 10 rooftops, and this is just examples of 2 different buildings that we modeled. This did prove to be a little bit more complex than the farm. So the farm, our spacing has to be about 2 feet apart from each of the rows of the panels, but our rooftop system was different in that we only used 80% of the available roof to model the production that we could get from these roofs, and this would account for losses like shading or fluctuations. Next slide. And here's a general power flow system model for our proposed design, and it differs a little bit from some industry practices. So we wanted to boost our efficiency and minimize losses, and that was kind of the guiding principle that ran throughout our entire design process. So sending DC supply straight to the controller and the battery first saves us 1 step of inversion losses. And our DC AC ratio, we used a more conservative amount of 1 rather than industry practice, which could be about 1.5, because the 1.5 prioritizes the first 5-year profits, and we chose to prioritize using the most of the energy that we could, and prioritize the overall financial benefit of the system rather than just the first 5 years. Next slide.
When sizing the proposed photovoltaic system in Las Cruces, there are many considerations that would drive our decisions. Some of these being the abundance of insolation, varying ambient temperatures, and campus energy demand. These were all factors that allowed us to establish a target goal and what our calculations would be based on. We were able to use hourly data from National Solar Radiation Database. This gave us ambient temperatures and global horizontal incidence. We were able to determine the efficiency of each panel used. Panels used in the farm are commercial grade and rated at 470 watts, which yield 17,403 panels to cover the entire load for the year. This was calculated using hourly data provided for 2018. Residential panels were chosen for the rooftop locations. These provide high efficiency paired with ease of installation, reliability, and expandability for the future. Next slide, please. When using OpenDSS, a MATLAB interface was used to integrate these two softwares. Upon modeling our system in OpenDSS, all of the buildings were provided with photovoltaic generation and connection to the nearest bus. After running the system, no faults occurred, and the PV generation for each building successfully compiles into the underlying infrastructure. Displayed are the kilowatt and kilovar profiles per each phase as a function of the distance from the substation. Also displayed is the circuit profile with the PV generation interconnected. Next slide, please. Our battery rationale comes from our drive to minimize power consumption from the utility by discharging the battery when the PV is non-operational. Lithium-ion battery storage is preferred, and all battery parameters are shown on the right. The battery has the ability to provide demand response or frequency regulation. In this case, the demand response management will be used more frequently as the battery is designed to discharge over a longer period of time. Next slide.
So here's our financial analysis assumptions, with the first one being our total PV cost for our system, and that came out to be about 12.2 million. And this data was gathered from Lawrence Berkeley Lab. And next is our battery cost, and those came out to be roughly 6.8 million, and that was gathered from Bloomberg NEF. And then next is our inverter costs, and those were about 750,000, and that came from NREL. Next slide, please. So this is our first case in our financial analysis, and this is from the perspective that the university is providing all of the financing for this. So our revenues were used as our cost savings, and then the money that we would get back from selling the power to El Paso. And then next, our expenses were the money that that El Paso would buy back from us, and then also our equipment. And this, after 20 years, this came out to be right under 7.4 million for the university. Next slide, please. And this case is involving a third-party investor. And I would like to highlight that our PPA came out to be about 4 cents per watt between both parties. And so our revenues were the PPA income, with our expenses to be the PPA payout as well. And so we took into account our depreciation expense to taxes, and year 9 is the only year that we had to pay taxes. So that was very, very beneficial. And so the total net income for the third-party investor came out to be right above 1.6 million after 20 years. And then the total cost savings for the university came out to be roughly about 4.5 million after 20 years. Next slide, please.
The building and site plan for Clemson's design has been carefully planned. The main areas on campus allowed for solar power is the rooftops of the buildings, where about 80% of the service area will be used. On top of this, a remote land area that's local to NMSU will be used for a solar farm as well. There are also zoning safety codes that are met with Clemson's design. Our main concerns were being safe for civilians while on campus and designing for sustainability, including things such as future maintenance and compatibility with an evolving grid. The tax parcels and grid easement will also be respected accordingly. Safety standards such as NESC and IEEE codes must be followed as well. On top of this, aesthetics is not an issue since the panels on campus will be out of sight with the exception of Goddard Hall because it has slanted roofs. All of the other buildings, they're flat, and being on campus, a civilian on campus won't be able to really see any solar panels at all. Next slide, please. As for the construction and development plan, El Paso Electric will be contacted for regulations. They will validate the compatibility of the design with the current power grid. For physical construction, the minimum amount of effective area would be used. Safety is also a large factor, and the hired contractor must adhere to the safety codes as well. At the most, the project could take a year from filing to the Public Service Commission of New Mexico. The community input will also be needed via a town meeting or a community meeting for consent. The project is financially viable if the local utility is the owner of the system, which means the risk of deployment would be relatively low altogether for things on the financial side and the safety side.
All right, so now it's time to look at the innovation and optimization involved in our project. Next slide. So some of the ways that we optimized our design was placing the inverters at the final DC output of the battery and using the AC-DC ratio of 1. The next way we optimized was our novel 60-40 approach to the design and power management. And we have overall accomplished the feat of making sure that the university has to buy back from the utility, but only at the off-peak times. And there's also evidence that our rooftop grid and our solar system can be scaled up for future use on the campus. Next slide. So our system also provides lasting energy management for with our charge and discharge rate of less than 1 cycle per day. Our lithium-ion batteries improve the power quality and they provide voltage and frequency support. Our ramp rates that result from PV fluctuations in the system and the demand charge rates will actually both be managed by the battery charge and discharge rates. Next slide, please. So in conclusion, during our exploration of providing solar solutions, we did show that a grid-tied system can absolutely meet all of NMSU's clean energy needs and save them quite a bit of money. In our detailed analysis that we've mentioned in our project, we also show that there is room for an off-grid system to be developed, even one at this massive scale on the NMSU campus. It's definitely feasible, and it could help them expand in the future to become completely energy dependent. And it could also have applications, we believe, for the electrification of transportation on their campus. But overall, when it comes to today, I think our grid-tied 60-40 approach with storage solutions, which is backed with the extensive analysis that we've done and the data that we've pulled from the NREL databases, that shows that the switch to clean energy can and should happen probably today. Next slide. Thank you all so much.